This episode is sponsored by Audible. In the future, humanity may come to reside on strange new worlds, and likely many will have lower gravity than Earth. We may find native life on those worlds or adapt them ourselves, but what would those adaptations be? There is a fairly common assumption in science fiction that folks living on low-gravity planets or on spaceships would tend to grow tall and willowy, while folks on high-gravity worlds would tend to be squat and muscular. On initial inspection, this seems to make sense. Trees have evolved to reach up high to get sunlight, above their neighbors and other plants, and are limited in height largely from issues like weight and fluid pumping, which are obviously reduced in lower gravity, so it stands to reason they'd be able to get taller if there was less gravity. Of course, they also need to be strong enough to resist wind, so where there is more of that, they can't grow as tall. When we consider places like Mars, with its infamous dust storms, we sometimes forget that those aren't actually very strong for the speed the air moves at, since the atmosphere is so thin. If the atmosphere is thinner, as we often expect on low-gravity worlds, this makes it even easier for a tree to grow tall. However, thin atmospheres are not a guaranteed thing on low-gravity worlds, and neither is a tree a very good analogy for an animal, let alone a human. Our catalog of planets besides Earth has grown massively in recent decades, numbering 1,000 times what it was in my childhood, but not only are most of the new worlds around distant suns little more than vague blobs we know little of, but they're almost all planets that are vastly more massive than Earth. It's easier to detect the bigger worlds after all because they block more light when they pass in front of their sun, make their sun wobble more with their mass, and noticeably change the gravitational lensing effects when their sun lenses a more distant star. But smaller planets may prove far more numerous when we can better detect them, and so far we really only have Mars, Venus, and Mercury to look at in terms of place with less gravity, and obviously none host any known life. There are 4 basic factors that make a planet keep or lose atmosphere. High gravity holds it in place, high temperature boils it off, ionizing radiation zaps it away a little at a time, and geomagnetic fields protect it from that ionizing radiation. But remember that an atmosphere is generally a mix of several gases, and the high molecular weight gases are easier to hold onto than the light ones. Venus illustrates this very well because compared to Earth, it's worse on every one of these factors: lower gravity, higher temperature, more solar radiation, and no magnetic field, and yet it has a thicker, denser atmosphere than Earth. To explain how low gravity works on Venus, we have Peter, the voice of What If. What If is a science show here on YouTube, where you explore epic hypothetical scenarios.
Hey Isaac, thanks for having me. So, how does low gravity work on Venus? Well, when low and high molecular weight gases are mixed, they reach the same temperature, but the high weight gases aren't moving nearly as fast. They may be high weight, but they're slow speed. Escape velocity, which is the speed needed to break out of a planet's gravity, is the same for any molecule mass, but far fewer of the slow molecules are able to break out of it. Earth actually loses little bits of elemental hydrogen and helium to space all the time, but it manages to hold on to heavier elements like nitrogen and oxygen. But Venus has lost those gases and holds on to much heavier ones like carbon dioxide, sulfur dioxide, trioxide, and some nitrogen. So, in theory, a low-gravity planet could have a dense atmosphere, but this means it would have to be composed of heavier gases than what we have on Earth. A magnetic field would definitely help keep the atmosphere in place, but as Venus shows, it's not completely necessary.
Thanks, Peter, and folks, make sure to check the link in the description and subscribe to What If. Back to low gravity. Given the timelines involved, a planet that has developed complex life is probably either going to have a pretty thick and stable atmosphere, or have long since lost all but a trace of it. There's no real reason it would have a thin atmosphere compared to Earth and yet be thick enough to permit surface water. Moreover, we can't really assume our solar system is a good model for this, as our sun is bigger than most stars, and also rather stable as these things go. Many stars will be far more volatile, while others might have less output in the more dangerous bands of radiation that would tend to ionize particles. For that matter, under lower atmospheric pressure, water boils at a lower temperature, putting more water vapor in the air that can be broken into hydrogen and oxygen, and that hydrogen lost. Whereas if the atmosphere is higher pressure, water evaporates at higher temperatures. You also need more air on low-gravity worlds to get the same surface pressure due to the lower gravity. Pressure is the cumulative result of weight of air, and weight is a function of gravity, so the same quantity of air on a lower gravity planet as Earth has would be at a lower surface pressure. We would also expect that atmosphere loss is a bit of a runaway process. As you lose more and more air, it goes faster. The pressure drops and the oceans evaporate easier, and particles hit by high-energy particles can travel farther into thinner air without hitting another particle to lose speed, and so you lose more pressure and lose air faster. Add to that, hotter planets are nearer their sun and hit by more ionizing particles and solar wind. So too, they are more likely to become tidally locked and have their metallic inner core slow down as a result, as those big spinning balls of molten metal that generate those magnetospheres, if that weakens, they lose air even faster. So we do indeed have reason to think low-gravity worlds and hotter worlds will lose air faster and be less likely to have an atmosphere by the time life of complexity has developed, but we also can't assume that's a hard and fast rule. Large moons around gas giants might be shielded in part by the magnetosphere of their massive parent world, for instance. Worlds around less volatile suns might get less pounded by solar radiation and wind. Planets might get hit more often by comets bringing more water and other materials in, and so on. They will be less likely overall to have thick atmospheres than bigger worlds, but they are also likely to vastly outnumber those bigger worlds, so it may be that the majority of worlds with oxygen-nitrogen atmospheres are actually worlds less massive than Earth simply by raw numbers. As I mentioned a moment ago, Venus is hot, has virtually no magnetosphere, and has slightly less gravity than Earth, yet possesses a very dense atmosphere, though much of this is heavier carbon dioxide. Beyond not wanting to assume life definitely needs water to live or oxygen to breathe, a world heavy in carbon dioxide might retain a higher pressure atmosphere while also being warm farther from its sun, as carbon dioxide is a greenhouse gas. Many other permutations of atmospheric composition are potentially plausible and viable too, and needless to say, this only applies to worlds with surface oceans and atmosphere. Many moons and lesser planets will have oceans beneath the layer of ice in which life might originate. We'll focus on the liquid water under an atmosphere case though. Now this all assumes a natural setup. When it comes to terraforming worlds, we could probably keep an atmosphere even on our own moon simply by setting up a powerful magnetic field around it. And it's easy enough to do. You don't need a big ball of spinning molten iron for this, and it's far easier to simply create a big solar-powered electromagnetic ring around such a moon or planet, as we discussed doing in springtime on Mars. It's a big task to be sure, but less than folks tend to think, and it doesn't require that much power, and is far easier than trying to drill down to a core and dump millions of megatons of atomic bombs down there, as folks often suggest for Mars. For comparison, it's like deciding your backyard gets too much wind and building a wall or hanging tarps to block the wind, versus trying to set off earthquakes and volcanoes to make a new mountain arise to block that wind. And of course you can always just go the construction route and cover a world with vast numbers of domes to hold air in, what we call para-terraforming. It sounds like quite a project too, but it is tiny compared to actual terraforming. So too, bringing in the occasional comet to hit the world, or get detonated right before hitting to avoid a big impact, allows you not only to add an atmosphere but refresh it if it's leaking a bit too much. And since it's mostly leaking hydrogen and a little bit of helium, the first and second most abundant materials in the universe, you're hardly in short supply of replenishment sources. As to oxygen, it is the third most abundant element in the universe, and most rocky planets are overflowing in it, tied up in those rocks. It usually makes up the first or second most abundant material of those places. You can easily remove it from those rocks for your atmosphere, and atmospheres are only a tiny part of the total mass of planets like Earth anyway. Needless to say, this is only allowed under artificial circumstances, planets we come to inhabit with our technology and industry, though we might imagine a number of interesting phenomena that might allow it to be natural. As an example, planets around red dwarf stars, the most common kind of star, might easily have their own robust Kuiper belts or Oort clouds full of icy comets. Water is ridiculously common in this universe due to hydrogen and oxygen being so abundant, and any such comets entering in close would have a shorter path between the frost line where they melted and impacting the planet, which also takes up a bigger effective cross-section for collision in that solar system since it's more compressed around that smaller, dimmer star. So they might get hit by comets much more frequently and replenish their gases that way. Now as to life living there, however it arose, natural or transplanted, what really is different? Again, it is likely to have a decently thick atmosphere or none worthy of note, so we shouldn't assume the natives need giant lungs, or that trees can grow however tall and broad they want without fear the wind will knock them over. What about the critters though? Are they more tall and willowy from the low gravity? Perhaps, but we have to ask why they would get taller. A tree has a reason to get taller. Tall is only advantageous in nature because it makes a critter look more threatening or reach food that's higher up, and there is a reason we don't really have as much megafauna as we used to. As to thinner bones and less muscle, one might ask why. Birds have thinner bones to make them lighter for flight, though hardly lack in muscle. That comes at a price of being less sturdy against blows. We need thick skeletons to support our mass and absorb the shock of falling and walking, but also to support us against inertia of hitting or being hit, and inertia is not affected by gravity, just weight. Nature also cooked up ways for critters to get big, like having air pockets in their bones, as large dinosaurs often had. Peter, are there any alternatives?
Well, a cool thing you'll find on a low-gravity planet is that you can have thicker bones, as well as more muscles compared to what you might have on Earth. This is due to your body weighing less. It'll still take effort to alter your inertia, but you'll weigh a lot less and be able to carry way more mass. And think how cool you'll look when you're at the gym. We can look at megafauna in the past who also benefited from higher oxygen levels. If we wanted to achieve similar pressure to what we have on Earth, we'd need more air, which would significantly impact the weather as well as the biology and chemistry on the planet. Flight is easier for creatures in lower gravity as well. Though flight mostly has to do with speed and air density, we could see massive critters flying about. Ugh, gross. Since gravity would affect swinging and jumping as well, we could also see a lot more creatures living in trees, engaged in branch hopping or even gliding. These wouldn't just be tiny little squirrels either. The creatures living in these trees could be massive. The reason why they aren't up there right now is because it's too dangerous for large predators to be up in tall trees, as it's too risky for them. With this low gravity, we could also see creatures who could parachute, as well as ones with wings. However, this low gravity could hurt smaller flying creatures like insects. These creatures rely on the air being thicker, which helps for flight and maneuverability, even in lower gravity. The new insects we find on a lower gravity planet would be kind of like dragonflies, only smaller. Or they might be microscopic. Creatures on a low gravity planet sure sound interesting, but what would happen to these insects if we lived on a planet with much higher gravity? Well, you can check out our episode, What If the Earth Was as Big as the Sun, right here. Back to you, Isaac.
That part about bones having air pockets in them from a moment ago might result in quite the opposite effect on tree height too, on higher gravity worlds. As we said earlier, hydrogen and helium escape fastest from planets, and gravity really does play a role in retaining gas. What's more, a bigger planet is likely to have a stronger magnetosphere to hold on to those gases. Such being the case, we might see higher gravity worlds featuring tree equivalents that made use of biochemistry to separate lighter gases from the atmosphere and used internal bladders of lifting gas to let them grow far taller, potentially even photosynthetic bladders as a leaf analogy. Such plants would still be vulnerable to wind, but they might be able to deflate themselves in wind and storms then reinflate. Of course, something like that could have evolved under any gravity. It really depends more on if the atmosphere's composition is rather spread out in terms of the mass of air particle types. Virtually all of our atmosphere is diatomic nitrogen and oxygen, and they are about the same mass, only a 14% difference, as opposed to diatomic hydrogen and carbon dioxide, where the latter mass is 22 times as much as the former. If it had large portions of gases that differed by much in molecular mass, such lifting gas approaches to weight might show up. Creatures that were essentially organic blimps that sucked in air and retained the lighter molecules to serve as a lifting gas. We do after all see it in regard to oceanic creatures, which frequently use air and water ratio changes to alter their buoyancy. Indeed, it is possible you might not simply end up with two ecological layers, ground and treetop, but an entire biosphere layer suspended in the air. If that lighter gravity world was maintaining its atmosphere in large part from having a big molten core and much tectonic activity, you might have a good deal of dust and moisture in the air, and organisms floating up there to maximize light and feed off those atmospheric contaminants to achieve both nutrient and buoyancy. In lower gravity, it's easier for wind to pick up dirt and soil and loft it into the air too. But speaking of dirt, we are not limited to going upward either. Much of our own ecology is beneath the ground, and is partially limited by the rising pressure and density of the dirt. You might have deeper topsoil just from a reduction in gravity and weight compressing things. Such worlds might have far more caves too. The moon has many large underground lava tubes, as probably would many smaller worlds, because they don't collapse as easily, and it is easier to dig through dirt or gravel and shore up tunnels in lower gravity. You might have far more burrowing creatures and far more large caverns as well. What we're seeing though is that gravity itself, while a major factor in how a world is set up, still leaves a very broad range of options available. Taken as a whole, I don't think we can make the assumption that critters would evolve to be skinny and large, though large seems plausible. Just in this case, large might also be muscle-bound brutes carrying a lot of bone. You might also tend to see more internal storage too, akin to the camel and its hump of water. Motion still takes energy and is mass dependent, but a lot of critters spend a lot of their energy just standing. You burn more calories standing than sitting or lying down, for instance, and that's purely a function of weight. But big also moves slow, even if it's got the muscle to run quick, because it's not very agile. It's very hard to turn on a dime when you're an elephant after all, compared to a mouse. As I said, many of the planets and most large moons that we will encounter in the universe will be smaller than Earth. We'd expect to find more worlds with less gravity than more. I suspect life, at least surface-based land life, to be more likely to exist where gravity was a bit higher, but it could be that the larger number of smaller worlds will make up for them being less likely to host atmospheres. But I also mentioned that while we were focusing on worlds with surface oceans and atmospheres, we would have a lot of such worlds where the water was trapped under a layer of ice, places like Jupiter's moon Europa. Such worlds would be scanty and meager in their life. There's just not much energy to run an ecology without the sun, but they may be quite prone to having life develop regardless. It's also a good reminder that our oceans are affected by gravity too, and not just tidal forces. Pressure is a function of weight above you, and that's lower if gravity is lower, so you might see quite an expansion oceanic layers. Now the top thin layer of water where light can reach abundantly is still where most of the action would take place, with much beneath it being those organisms living on debris, marine snow, descending from that top level. That might see some interesting adaptations toward the vertical. Near the shore, we often see plants that grow on the seafloor, getting nutrients there, but reach up to the top for light. Out in the deeper sea, things either live on the bottom without light, or up top with light but little nutrients. In lower gravity, that shore zone where they can reach from the seafloor to the top is expanded as plants can grow taller and reach from the seafloor to the surface further from the shore. Possibly a great deal, as traits that improve that option would probably be more easily favored by evolution. You might see plants growing rather tall in the sea, moving your coastal ecologies out much deeper. However, nutrients that are heavier than water also sink faster in higher gravity, so we might tend to see more abundant ocean life. Most of Earth is covered in deep sea. Life is not terribly abundant there compared to the shores or inland, because sunlight is up at the top and nutrients fall below, or scarcely diffuse into the water near the surface. If it's easier for nutrients floating in the water to persist near the top, then more biomass would arise in those areas away from the coastline. Combined with lower pressure, this might result in very verdant oceans, potentially clogged with life on the surface so that you could literally walk across the water. Hard to say, of course, and this is all very speculative, but we see a door open to far more ecological options than we might initially expect, compared to the usual notion of thin, dusty, dry worlds of low gravity. Of course, that is very dependent on having a thick atmosphere, and as mentioned earlier, once one of those begins dissipating, it probably is a bit of a chain reaction, losing air faster and faster. Such things would still be on geological timelines, so life might adapt as the air thinned and oceans diminished. Until the early 20th century, we thought Mars had canals left over from ancient oceans, and while better telescopes have revealed that those barely visible lines were just surface fissures, it also appears that Mars did have oceans and an atmosphere long ago. Hopefully someday soon we'll get to do some serious excavating in geology there to see how long ago it was, and how quickly it ended once that atmospheric loss hit critical tilt. There's a lot of books set on Mars, of course, and while modern ones usually focus on us colonizing it and bringing life there, those of a few generations back tended to assume life was already there but diminishing, that Mars was dying off. We see one such example in C.S. Lewis's Out of the Silent Planet, the first book of his space trilogy, our Audible Book of the Month. C.S. Lewis is best known for his classic fantasy series, The Chronicles of Narnia, which along with his friend J.R.R. Tolkien's Lord of the Rings, helped breathe life into the emerging fantasy genre. But over a decade before Narnia, he wrote the Space Trilogy, and its protagonist, philologist Elwyn Ransom, is said to have been modeled on Tolkien as an inspiration. I happen to have gotten an omnibus edition of the trilogy as a Christmas gift from my fiancée Sarah, who promptly borrowed it to read on a trip, leaving me to need to grab the audiobook version instead, which to be fair is my preference as I quite prefer listening to tales anyway. Unsurprisingly, it inspired today's episode. While the science is of course dated and never was C.S. Lewis's strong point anyway, the first book paints a fascinating portrait of the Red Planet and the life that emerged there, the culture and language that developed, and the philosophy of colonization of other worlds. Audible has an amazing catalog of audiobooks, and Audible members can choose 3 titles every month, 1 audiobook and 2 exclusive Audible originals you can't hear anywhere else, including access to news, original audio shows, and guided fitness programs. And since you can listen to your audiobooks anywhere on any device, and seamlessly pick up where you left off, they're great for commuting, running errands, or going to the gym. You can start listening today with a 30-day Audible trial. Choose 1 audiobook and 2 Audible originals absolutely free. Just visit the link in the episode description, audible.com/Isaac, or text Isaac to 500-500. So we have our monthly livestream coming up this weekend, Sunday, March 29th at 4 p.m. Eastern Time. And then we'll move into April's lineup, starting with a look at new technologies that might be in the cards in the coming decades. Then 2 weeks from now, we'll flip that around and ask ourselves what things might be like if technology came to a standstill, and what might cause that in technological stagnation. Don't forget to check out the video, What If Earth Was As Big as the Sun, over on What If, and subscribe to their channel. And of course, don't forget to hit the like button and subscribe to this channel if you enjoyed today's episode. And remember, we've got our monthly livestream coming up this Sunday. Until then, thanks for watching, and have a great week.